Okay, thanks, Ron. So I'm Greg McDermid. Ron asked me to come and speak to you all about some of the research we've been doing in the boreal forest as part of a project called the Boreal Ecosystem Recovery and Assessment Project, or BERA. So BERA is a project that's sort of using geospatial technologies like drones to look at the impact of human disturbances in the boreal forest and to look at strategies for trying to restore some of those disturbances. I just have my own name on the slide deck here, but I want to emphasize that this is not just me. There's plenty of authors that I'll be going through their work. I'm just going to probably do it as I go along. There's 3 universities involved in this and several industrial partners. So when people think about remote sensing, I'm going to start with a few basics here. Any basic remote sensing class will show you a photo like this, and they'll say, look, there are several platforms for doing remote sensing. We have satellite platforms that are way up in the atmosphere, above the atmosphere. We have piloted or manned aircraft that fly either low or high above the ground. And then we have ground sensors or ground platforms. And you can put any type of sensor you want on those platforms. So that's basically what we have in terms of our remote sensing toolkit. And I think that these graphics are meant to show that we've kind of got it all covered. But that really wasn't the case. The piloted aircraft fly very high above the ground, honestly. So I think that this UAV drone platform is one of the most exciting things in remote sensing. It's a whole new platform that fills a very large niche that I think was previously missing. There's lots of constraints that we've heard about today and we'll continue to hear about, but sort of moving forward, I don't think it's going to be too long until this platform, the UAV platform, will dominate remote sensing because of what it's able to do and because of the significant advantages in savings, cost savings. It's like the democratization of remote sensing, in my opinion. What I want to do, though, is I want to really separate the platform with the sensors and the sensor technology. Those are 2 completely different things, and I don't want you to confuse those 2 things as we sort of move through the day. So I'm going to reinforce some of the things that Guillermo said this morning. So these are some of the common sensors that we mount on platforms of any type, including drones. First of all, there's just cameras. So the type of cameras that you have in your pocket, we can mount them on things. We can use them for 2D mapping, orthophotography. We've seen some stereo imagery, photogrammetry applications. These are all done with cameras. The thing that makes cameras good for drones is this is a very mature technology. You can rely pretty well on this type of sensor technology. There's other types of sensor technologies that people are flying on drones that are not as reliable. So for example, I would consider the multispectral or hyperspectral sensors. These are the sensors that go beyond visible light into the infrared or even beyond. This is technology that needs to be miniaturized before you can mount it on a drone. And so maybe that's not really where we need it to be in order to trust the data. I would consider this a developing technology. Same with LiDAR. LiDAR is probably our most reliable way of doing 3D remote sensing. It's an active remote sensing technology. But again, these sensors have been developed to be large, to be mounted on piloted aircraft or used on the ground. If we have to miniaturize them and put them on drones, we're still developing that technology. I would consider it not quite reliable yet, although this is moving quickly. There's many others. I'm not going to go down the full list. Microwaves and radars is a very common remote sensing technology or remote sensing instrument, but outside of navigation purposes, it's really undeveloped in terms of imaging when it comes to drones. Then there's what you do with the data. I'm going to limit my comments only to the optical data, which I think this is the cameras. This is the stuff that I think is most reliable from a drone perspective. But we can treat that data in a number of different ways. First of all, you could, when you just look at your basic drone photography, it's got a lot of distortion in it. This is called parallax. You can see the trees leaning away from the center of the photograph. We can process that data and we can make it planimetric so that you can map against it. So this lower scene has been processed with the magic that was described earlier so that now you can make an ortho image from it and you can sort of use some common spectral analysis routines and do some stuff that way. But that's really a 2D technology. You can map the length and width of things, but that's really what you get from orthophotography. You can also use something called structure from motion. This is something that Guillermo didn't have the time to cover this morning, but this is a workflow where you can take the same photography that you use to make the ortho photography, and you can extract something that is a point cloud. It looks superficially like a LiDAR, and a lot of people treat it the same as a LiDAR. It is 3 dimensions. This looks like a photo, but it's not. It's a series of hundreds of thousands, possibly even millions of points whose positions are precisely known in 3 dimensions. But it's only superficially like a LiDAR. I don't have time to go into the details, but there's some significant differences between this data set and what we might be used to with a LiDAR. I'll just point out one quick thing. This is a passive technology. We're only taking photos of the surface. We're not shooting laser beams down there. So you can see that it doesn't have the ability to penetrate the canopy like you get with a LiDAR. So a lot of stuff below dense canopy will be sort of dark. So you have to think about this when you're going to extract your metrics. Is this limitation going to be, serious or not? The third thing that I think we need to think of as really possible with this type of drone photography is just good old school soft copy photo interpretation. Sitting in front of a soft copy workstation with your avatar goggles and using that 3D information in a different way. Also very, very powerful. So sorry for the little dispersion there. We use all those types of processing to do our work in BERA. I'm sort of going to limit my comments primarily to restoration of seismic lines. We work in the boreal forest, and so this is the dominant human footprint type in the boreal forest, though certainly not the only one. And so we're sort of basing our research on this new provincial restoration framework that's designed to, restore legacy seismic lines. So the older, wider seismic lines that are very common in the boreal forest. And basically, essentially what they're trying to do is restore these things for the purpose of caribou primarily. So encourage a return to forest cover and then limit human and predatory movement on the landscape. So there's a number of targets which we're trying to develop workflows with drones in order to try and address. So for example, seedling detection and stalking. Can we find seedlings on these seismic lines, and then can we do stalking assessment using drones? Part of stalking assessment will be measuring the heights of these things. So can we measure vegetation height reliably using some of these workflows? Coarse woody debris, limited predator movement, micro-topography. So can we make digital terrain models that capture some of these important micro-topographic features? Groundwater, this might be something that you didn't expect. Can we use drones to map subsurface water? And then canopy structure and opening. So to me, the thing that's interesting about UAVs is, despite their current limitations, I see this as sort of a supplement or a complement to field work. It basically complements what we do boots on the ground right now, as we heard in the previous presentation. And it allows you to do some things that you probably couldn't do with boots on the ground. And I think I got a little bit of examples of both on this list. So I could easily fill the whole morning here. I'm sure Ron is going to be cutting me off, so I need to go quickly. I'm not going to talk about all these things. I'm just going to pick a few and give you sort of a high-level introduction as to what we're learning about using drones to look at these targets. So the first one I'm going to talk about is seedling detection. So finding these regenerating seedlings on human disturbance features. So we asked a simple question: can UAVs use to rapidly identify these regenerating seedlings? Now, we didn't want to use fancy technology. We used a simple consumer-grade camera and very straightforward image handling. Nothing fancy going on here. And we also looked at very, very small seedlings. So these were seedlings that are only 4 years past planting. So, 15 to 30 centimeter tall seedlings. So a very challenging application. We didn't fly wall to wall. I think that one of the real benefits of drones is that you can just sample with them. You could just send your drone up over to a spot, and our drone would go over there, and then it would descend using a little laser rangefinder to a certain height above ground, take a photo, go back up, and go over to the next measurement station. So it just basically flies around like this. It really simplifies things. Every time it takes a photo, this is what it sees. So essentially what we did is we set up these experimental plots, these little round circles that you see, and we went out there with a survey grade GPS, and we recorded the locations of all the seedlings, which are the little red dots within these plots. And then we simply wanted to see, could the imagery find those seedlings? We did some pretty basic processing. We essentially, you can see the seedlings here, by the way, in the raw photos with the dots on them. We segmented the images into objects, and then we used some machine learning decision rules to just pull out the objects from their surroundings, the seedlings. Does it work? It works pretty well. 75% overall accuracy. We used independent test data. So we trained our classifier in one area, and we tested it in another physically removed. It was actually hundreds of kilometers removed. So this was a pretty robust test. So 149 plots, 75% overall accuracy. We did have a slight tendency to underestimate seedlings, especially when densities were quite high with natural regeneration. We didn't see that as a serious limitation because if you're doing stocking, underestimating is probably not a bad place to be rather than overestimating. And what we found is that our ground observations were very, very highly associated with our drone observations. So Pearson's R of 0.98. The big limitation here, I would say, is it relies on a pretty narrow phenological window. You can tell by the photos, we're flying in early spring conditions where nothing is green on the ground except for the conifer seedlings. So this is why we're able to do it with really simple technology, consumer grade cameras, nothing fancy at all, because we're relying on this narrow little phenological window. So, moving quickly, can UAVs be used to rapidly identify regenerating coniferous seedlings using consumer-grade cameras and straightforward image handling? Yes, that's been our experience in Alberta. However, like I said, our workflow relies on this fairly narrow phenological window. If you tried this in midsummer when there's lots of green things down there, I don't think you'd get the same results. There's also some other observations, but I don't have time to go into too much. I think that different seedlings behave different ways, different species, and we think that should you run into other species, you need to probably follow some slightly different workflows. There's a paper on this that my student Corey Fedek, this is his master's research. So if you want to know more about this application and our findings, this would be your source for it. I'm sorry, I'm moving quickly here. I now want to get into some of the 3D technologies that's been shown. The previous study was just using simple photographs that we really didn't do anything to. This is one of these photogrammetric workflows where we run it through the structure from motion technology, the magic that's been referred to before, and it produces a point cloud that allows you to do 3D remote sensing. So we dove down into a seismic line and we flew along the seismic line in the data set. We didn't fly the drone down here, we're just flying around the data set. And you can see this is a very narrow seismic line. These are very small seedlings. That's a hula hoop there in the middle with a tape measure running across the middle. So very, very high quality data. So the question is, if we're going to be doing stocking and we need to know how big are the seedlings, first we need to find them and then we need to measure them. So the question now is, what sort of 3D information about vegetation height can we get from this type of data? So that's my second target, vegetation height. We again asked some pretty simple questions. Can UAV photogrammetry be used to measure vegetation height on seismic lines? I've told you about this limitation where we don't reliably get the ground with photogrammetry. So one of the workarounds is that you use pre-existing LiDAR to get the ground. And then you basically just get your first return using photogrammetry. So we asked the question, do you need to have supplemental terrain information from LiDAR, or could you do it just straight from drones? And then how much does it cost? So again, I'm sorry I'm moving very quickly through all of this. We essentially laid out a series of measurement stations along 150-meter stretches of seismic lines. So we have these transects running down the seismic line stretch, and then we have these 3 cross sections, and essentially we set up little measurement stations along those transects. And what we would do is we would survey our location using a very high quality GPS, and then we would see how high is the vegetation at that spot. So we essentially use a little pole, and we look to see where the vegetation touched that pole at that spot. And it might have touched at a number of locations, but we're only concerned with the topmost touch of the vegetation. So we essentially produced a ground-based manual point cloud using this very simple technology and compared it to the point clouds that we get using the drones. So here's an example of a seismic line. You can see some of our cross transects there. And then these little scatter plots basically show the comparison of what we measured in the field in terms of vegetation height from what we got from our point clouds. And you can see that there's actually 4 lines there, one of which is the ground measurements. And then the other 3 are UAV-based measurements that we corrected or uncorrected using LiDAR to some extent or another. So I'm not going to get into the details of this. I'll sort of summarize. Basically, we found that there were some differences from one measurement station to the next, but if all you're trying to do is see what's the mean vegetation height on this stretch of seismic line, then our UAV data can show you to within about 8 centimeters of what the boots on the ground people would measure. So that's very good accuracy overall. In fact, we showed that there's actually no statistical difference between what the field boots on the ground people are doing and what the UAV is doing if we're looking at sort of a section of ground, a section of seismic line. We actually didn't find any significant value to using LiDAR to find the ground. It is a little bit better, but we found that really it's good enough just to fly with the drone. The added benefit of incorporating the LiDAR is not worth your time if you're just looking at general vegetation height. So again, moving quickly here, I'll just answer the questions. Can UAV photogrammetry be used to measure vegetation height on seismic lines? Yes, particularly if you're just trying to look at general vegetation height. We found that our estimates were statistically identical to boots on the ground field measurements. Do you need supplementary information from LiDAR? Our experience is no in this situation. We did a little bit estimate of how much it costs, which I'm afraid I don't have time to go over the details of, but we found $350 per site for a 30-site survey. And so if you compare that to what it would cost to get your boots on the ground folks out there, it's a substantial cost savings, about 40% over traditional vegetation surveys. And again, I know I'm moving super quickly here. So there's another publication in the journal Remote Sensing led by Shizhuan Chen, who is my student who led this work, and you can go there for more information if you're interested. How am I doing for time there, Ron? 12 minutes. Well, I could have done 5 more things. I'm just kidding. Okay, I'm going to now probably butcher some of the work that comes from Guillermo's lab at the Canadian Forest Service, who's been my partner through much of this, by the way, he and his team. We wanted to see not just general vegetation height, but can you actually measure the height of the seedlings on these seismic lines? So this is actually from that little fly-through that I showed you before. You can see the snow on the ground, which I failed to point out in the fly-through, but it was there. And here are some clusters of regenerating seedlings that we can look at above from the imagery. Now, what we want to do is look at this structure from motion point cloud and see, can we measure the height of these particular seedlings using that data set? And so Guillermo's crew has been flying UAVs at a variety of different heights to produce point clouds of a variety of different densities. We want to know what's the trade-off between point cloud density or flying height and our ability to do this measurement. And you can see that as you fly a little bit higher and higher, your point cloud doesn't quite capture this little clump of seedlings as well as you might expect. This is part of the limitation of structure from motion, which again, I'm afraid I don't have time to go into, but you can see that things degrade a little bit as you get a little bit higher, further away from your target. Uh-oh. In general, though, there's still a pretty strong linear relationship. To summarize, we tend to underestimate heights a little bit using this technology, but still it's a consistent bias, so you can sort of account for that. So I think that there's good news here, is we may not measure the absolute height of these seedlings using the point clouds, but we're sort of consistently underestimating, so you can account for that bias. I hope that's a fair assessment. I want to move on, though, into things that maybe you might not have thought of when it comes to using this type of technology. So doing things that even the boots on the ground people can't do. Microtopography, for example. A lot of the boreal forest is made up of peatlands, where this sort of pattern of hummocks and hollows is a very important part of the landscape. So when you're trying to restore things, you need to account for that hummock and hollow landscape. So we wanted to know, can we use this sort of cool 3D point cloud high density data from drones to measure this technology? So we looked at some peatlands, some bogs up near Peace River, and we wanted to know, could it be done under sort of a variety of real world conditions? Not only can we find the ground, but then would use that data to classify things into hummocks and hollows, which is what the peatland restoration people really want to know. And also, we again asked the question, do you need the supplementary data from LiDAR? Or could you do this solely from just the photogrammetry from drones? So essentially what we did is we sent students up there with an RTK to measure the ground location and elevation under a variety of different sort of complexity conditions. So bare areas, sort of low complex areas, all the way up to very complex with lots of trees and vegetation around. We did this for 678 locations where we precisely surveyed the location of the ground. And then we just compared them to what we got from the drones. We essentially found that the root mean square error, so our average error essentially, ranged from about 14 centimeters to 42 centimeters, depending on how complicated the surrounding vegetation was. For everything but the most complicated class, our errors were in the 15 to 20 centimeter range. So that's pretty good. That's very good, actually. We found that the supplementary LiDAR, again, did not significantly improve our results. And we could use drones sort of as a standalone technology. The reason, I think, is probably because the type of LiDAR that we get provincially, normally, doesn't have the same point cloud density, and it's harder to pull it in together, so that incremental benefit is not really there for most applications. This is just a little example. This is a transect that we surveyed, and you can see the black line is what the RTK, the ground survey, showed. You can see the hummocks and hollows. The two lines above it are, the blue one is the UAV photogrammetry data, and the red one is the LiDAR data. So you can see that, again, we have a bias. We're not truly getting to the ground with photogrammetry. We're sort of measuring the vegetation on top of the ground, but it's a consistent bias. It mimics what's going on with the true terrain. So that's why the additional benefit of getting a LiDAR is not really there for some applications, like this one. So now we have these very, very accurate representations of the terrain, where we can remove the vegetation with processing. So this is the true ground for a tiny little patch of our study area up near Peace River. In fact, you can see the low impact seismic line running straight through there. You can see the hummocks and the hollows of the microforms. I could even see the tracks on the ground that the equipment used when they cut it. So this is extraordinarily detailed data. But what we want to do now is actually classify that into hummocks and hollows. So we made a reference surface. We essentially ran a low pass filter over the data. And then we basically said, if you're above the reference surface, you're a hummock. If you're below the reference surface, you're a hollow. Really, really simple processing. And we're able to make a map from that of hummocks and hollows, microtopography. Compared that to field measurements again, and it's really good. 84% overall accuracy in our classification of hummocks and hollows. And our errors were mostly for really, really small microforms. If the microform is pretty substantial, we get it very, very well. So this is an example of doing things with drones that you honestly couldn't do with boots on the ground. Again, just to summarize, can photogrammetry capture terrain elevation under a variety of conditions? Yes, I think this works well under all but the most complex conditions. As long as you don't have too many trees overhead, this is a good technology. Can this terrain elevation be used to classify microforms? Yes. Do you need supplementary information from LiDAR? No, not for this application. That's our experience, at least. Once again, if you're interested in more of this, there's a publication. This is Julie Levitt's work from our lab, and you can read all the details in this paper in remote sensing. My last target here is something that I think even we didn't think we're going to be able to do, and that was to map groundwater. And this is a really rare target for remote sensing because it's under the surface. How in the world do you map something that you can't even see with an Earth observing technology? We did this in peatlands, and this is a unique environment. This is what the boreal forest looks like. There's a lot of wetlands up there. And if you can make a few assumptions, then I think that this shows you how you can perform something with drones that you probably couldn't do with other types of remote sensing. So here are our assumptions. First of all, we assume that peatlands are internally porous with flat or gently sloping water tables. Second thing is we want to do this in a place where there is abundant surface water. And we assume that that abundant surface water is tightly linked to the groundwater. So if you can find the surface water, then you can infer where the groundwater is going to be. And finally, we need to be able to map these surface water features accurately in 3 dimensions, not just where they are X and Y, but what's their elevation as well. So this is something we can do with a combination of technologies and drones. So this is little tiny pieces of our study area, and the blue stuff is the water. So sometimes we have sort of big ponds, but even in the trees, you can see some trees here, there's tiny little pockets of surface water. It's everywhere up there. So this is a little 61 hectare study area that we did this work in. Here's a road running through here, and you can see some slight impacts of seismic lines and a pipeline running through. You can't see it at this scale, but there's water everywhere in here. So what we did is we used this very high resolution photography to sort of systematically look for water. So the red points here, the red dots, are locations where we mapped water. We extracted its elevation using the photogrammetric data, the 3D data, and then we're able to interpolate the spaces in between. So this is sort of iso lines and a shaded relief surface that shows where we think the groundwater is sitting in this study area. So does it work? Well, we drilled 31 water wells, temporally consistent water wells, and we found that our average errors were in the 20 centimeter range. So again, this works. The interesting thing about this is if you combine these last 2 technologies, we know where the ground is. We know where the water is under the ground, so you subtract one from the other, and you have something called a depth to water layer. And this is a really high value piece of information that you couldn't get from any other technology, again, showing the potential for drones. So to summarize, can photogrammetry used to measure groundwater levels in peatlands or other types of wetlands? I think that yes, if you make a number of assumptions and to the extent to which those assumptions hold. Internally porous, flat or gently sloping water tables, wetlands, these are the kind of conditions where I think we could do this sort of thing. Again, I know I've moved super quickly here, so there's a paper by Mustafi Rahman et al., who is again the lead author on this study if you want to know more information. So I'm going to summarize. I know this has been a bit of a whirlwind tour. I do think that UAVs fill a critical gap in near-surface remote sensing, which has been a long time coming. And really what it's going to do is it has the capacity to complement what we do boots on the ground. In some conditions, it actually supplements what we can do boots on the ground, but I would lean more towards the complement side of things. But I think I showed you a few examples of things that you can do that you really can't do with boots on the ground. So here are the targets that I would suggest we've done some work on, and it's got some promise, some of which I wasn't able to cover today in my talk, but I'm happy to talk about it later. My warning to you is that this is an emerging platform. It's emerging, so the technology around it is also emerging. I think that practitioners need to be wary about developing or underdeveloped sensors that we put on this platform. That's why we work primarily with the optical data from consumer cameras. That's pretty mature technology. Other stuff is going to come, but just be careful out there. So that's all I've got for you this morning.